Hey everyone, welcome back to the channel. In this masterclass, we are doing a complete, from the ground up deep dive into Java Introduction, JVM, JDK, JRE and bytecode. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. These are not introductory concepts to skim past. The JVM, bytecode, the JDK, and the JRE are the concepts that separate engineers who write Java from engineers who understand Java. Every deep problem, performance tuning, polyglot architecture, senior interviews traces back to this foundation. These three scenarios are real. In each one, a vague understanding of execution mechanics leaves you guessing, copying JVM flags from Stack Overflow, nodding at architectural decisions you cannot justify, or stalling in a high-stakes interview. Deep, accurate knowledge eliminates all three problems. This is the leverage point. Once you genuinely understand what the JVM is and what bytecode represents, you do not just understand Java, you understand every language that targets the JVM. Kotlin calling Java libraries, Scala running alongside legacy code, JVM producing native images, all of it follows from the same underlying model. Quick pause. If this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. The three acronyms form a strict containment hierarchy. The JVM is the execution engine, it knows nothing about source code, only bytecode. The JRE wraps the JVM and adds the standard class libraries your code depends on at runtime. The JDK wraps everything in the JRE and adds the development tools, the compiler, the debugger, the profiler, and utilities like JVM that let you inspect bytecode directly. The practical split is, if a machine only needs to run your application, it historically needed the JRE. If a machine needs to compile source code, it needs the JDK. Since Java 11, Oracle, and OpenJDK stopped distributing a standalone JRE, the JDK is now the standard distribution artifact, and tools like JLink let you package a minimal custom runtime for deployment. The journey from source to execution has two distinct compilation steps. The first is JAVAC, the Java compiler, which translates your source file into a .class file containing platform-neutral bytecode. The second happens inside the JVM at runtime. The JIT compiler watches which bytecode paths are executed frequently and compiles those hot paths directly to native machine code for the CPU without you touching a flag. Bytecode is the key to write once, run anywhere. It is an intermediate representation defined by the JVM specification, not tied to any real CPU. Because Kotlin, Scala, and Java all emit the same .class bytecode format, a Kotlin function and a Java function are indistinguishable to the JVM at runtime. That is precisely why Kotlin can call Java libraries with zero overhead both compile to the same bytecode contract. Java is one of those words that gets used to mean three completely different things simultaneously. We are going to cut through that ambiguity right now, building a precise mental model of how the language, the virtual machine, and the runtime environment all fit together. Precision here pays dividends every time you debug a production JVM issue or make a deployment decision. The Java language specification defines what Java code means, grammar, types, semantics, independently of any compiler or runtime. The Java platform is what actually executes your program, the JVM and the standard libraries. The ecosystem is everything else that has grown around those two foundations. Conflating these three levels is the root cause of enormous confusion, so keep them distinct in your mind from this point forward. The JVM is first and foremost a specification, a document describing an abstract computing machine with its own instruction set and memory model. Because it is a specification, multiple independent implementations exist. Hotspot is the reference implementation that ships with OpenJDK and is what almost every production workload runs today. OpenJ9 trades peak throughput for faster startup and a lower memory footprint, which matters enormously in containerized environments. JVM can compile Java ahead of time into a native binary with no JVM overhead at startup. Azul Zing's C4 collector eliminates the GC pause spikes that cause latency outliers in latency-sensitive services. When you tune JVM flags in production, You are communicating with a specific implementation, not with the specification itself. The JVMS says nothing about -XX, plus use G1 GC or -XX, max heap size, those are hotspot inventions. This is why a flag that works perfectly on hotspot may be silently ignored or may not even exist on OpenJ9 or GraalVM. Treat JVM flags as implementation-specific configuration, and verify them whenever you change JVM vendor or major version. The JRE is not a specification, it is a concrete, downloadable distribution. Its job is to provide everything needed to run a compiled Java program, a JVM implementation, the standard library your code depends on, and the configuration files the runtime needs to function correctly. Historically, end users installed the JRE to run Java applications without needing any development tools at all. Starting with JDK 11, a separate JRE download ceased to exist. The JDK fulfills both roles. For production container images that need to stay lean, the answer is JLink, introduced in Java 9 alongside the module system. With JLink you analyze exactly which modules your application uses and produce a stripped-down runtime image containing only those modules. The practical outcome is dramatically smaller container images, faster pulls, and a reduced attack surface, all without sacrificing the full power of the JVM at runtime. The JDK, JRE, and JVM are three distinct but nested things that developers often conflate. We will draw sharp boundaries between them, then move straight into bytecode, the artifact that makes the entire Java platform work. The JDK is a distribution package. It contains the full JRE so your code can run, and it layers a rich set of tools on top. Javac is the compiler you will use constantly. JVM is the disassembler we will use live in a few minutes. JMC and JConsole give you deep visibility into a running JVM, memory, threads, garbage collection, all in real time. The mental model is strict containment. The JVM is the execution engine. The JRE wraps the JVM with the core class libraries needed to run any Java program. The JDK wraps the JRE and adds every tool a developer or operations engineer could need. Developers install the JDK. Production servers typically run the JDK too, because diagnostic tools like JConsole and JMC are invaluable in an incident. Bytecode is the glue that holds the entire Java platform together. Every decision about portability, security, and performance ultimately traces back to this one artifact. Understanding bytecode is not optional for a serious Java engineer, it is foundational. Platform independence is not marketing, it is a precise technical property of the bytecode format. The instruction set bytecode uses is defined by the JVM specification, not by any CPU vendor. When the JVM executes bytecode on Apple Silicon, it JIT compiles to ARM64 instructions. On an Intel Xeon it produces x86-64. The bytecode itself never changes, only the JVM's output does. This pipeline is the central mechanism of the Java platform. Javac performs lexing, parsing, type checking, and code generation to produce bytecode. The JVM class loader pulls that bytecode in at runtime. The interpreter begins executing it immediately, while the JIT compiler profiles hot methods and recompiles them to native code for peak throughput. Every stage of this pipeline is worth understanding deeply, and we will cover each one. Bytecode is not a vague intermediate format, it is a fully specified instruction set for a stack-based virtual machine. Every opcode is defined in the JVM specification with exact semantics. That means bytecode is deterministic and verifiable, which is why the JVM can enforce security guarantees before a single instruction executes. We are about to open a real .class file with Java and read those instructions directly. We have talked about bytecode as an abstraction, now we read the actual bytes. Using the Java disassembler that ships with the JDK, we can see exactly what the JVM executes. This is the level of understanding that separates engineers who use Java from engineers who truly know it. We start with the simplest possible case, a method that adds to integers. Nothing here is contrived, this is real production logic stripped to its essence. Compile it with javac hello.java, which produces hello.cls, and then disassemble it with javac c hello.cls. 4 instructions. That is everything the JVM needs to add to integers and return the result. Each instruction maps directly to one operation on the operand stack. Notice there are no register names, no EX, no R0, because the JVM is a stack-based virtual machine, not a register-based one. Walking through the stack transformations makes the execution model concrete. Load_0 pushes parameter A, load_1 pushes parameter B, iadd pops both, adds them, and pushes the result. Ireturn pops that result and hands it back to the caller. Every JVM instruction is defined in terms of what it pops and what it pushes, that is the entire execution contract. The JVM is typed at the bytecode level, the type of every operand is encoded directly into the opcode name. A load means load an integer, a load means load a reference. This is not just naming convention, the bytecode verifier reads these prefixes to guarantee type safety before any code runs, making runtime type errors structurally impossible in verified bytecode. A conditional introduces two new concepts, a branch instruction and the constant pool. Ifl means if the top of stack value is less than or equal to 0, jump to byte offset 11. If n is greater than 0, the condition is false, so execution falls through to LDC, which loads a constant, here the string literal positive, from the constant pool embedded in the class file. Return then returns that reference. One subtlety that trips people up, the numbers in the JVM output are byte offsets from the start of the method's code, not sequential instruction indices. Ifl consumes 3 bytes, 1 for the opcode, 2 for the branch target, which is why the next instruction appears at offset 4. Understanding byte offsets matters when reading stack maps, debugging the compiler output, and answering the kind of deep JVM questions that appear in senior engineering interviews. We close this masterclass by walking the complete Java compilation and execution pipeline stage by stage. We will also dissect the binary class file format so you understand exactly what the JVM reads before a single instruction executes. Every .class file opens with the magic number CAFABAB, 4 bytes that identify a valid Java class file. This value has been unchanged since Java 1.0 and was chosen by James Gosling himself. Immediately after the magic number come the minor and major version numbers, followed by the constant pool, then the class metadata, fields, methods, and attributes. The major version number is the JVM's compatibility gate. Before any code runs, the JVM reads 2 bytes from the class file header and compares them to its own maximum supported version. Compile with Java 17 and run on a Java 11 JVM and you get unsupported class version error. The JVM saw version 61 but only supports up to 55. Use the JVM release flag to target older class file versions and maintain backward compatibility. This is one of the most commonly searched Java errors, and now you know exactly why it occurs. The JVM reads 2 bytes, does an integer comparison, and throws if the class file version exceeds its own maximum. The release flag on JVM lets you produce a lower version class file from a newer JDK, which is how library authors ship artifacts compatible with older runtimes. The constant pool is a lookup table embedded in every class file. String literals, class names, method signatures, and numeric constants all live here. Bytecode instructions never embed text in line, they store an index like number 7 which the JVM resolves at runtime. Entry number 7 is a string that itself points to the raw UTF-8 entry number 27. Code obfuscators work by rewriting these UTF-8 entries, and string.intern relates directly to how the JVM manages these pooled string references. Every professional Java developer should be able to describe this pipeline without hesitation. Source code enters the Java compiler and exits as platform-neutral bytecode. The class loader brings that bytecode into the JVM, the bytecode verifier validates its safety, and then the interpreter begins executing it. As the JIT identifies hot methods, it compiles them to native machine code, giving Java its characteristic warm-up followed by near-native throughput. The Java compiler lives in the JDK and transforms .java files into .class files through 5 distinct phases. Lexical analysis breaks raw text into tokens. Parsing organizes those tokens into an abstract syntax tree that represents the program's structure. Semantic analysis resolves names and builds symbol tables. Type checking enforces Java's static type guarantees. Finally, Bytecode generation walks the AST and emits the JVM instruction sequences we explored earlier. Once bytecode reaches the JVM, the class loader hierarchy locates and loads it. The bootstrap loader handles core Java classes, the platform loader handles extensions, and the application loader handles your code. The bytecode verifier then performs a static analysis pass to guarantee the code cannot perform illegal memory access or corrupt the JVM. Execution begins in the interpreter, but the JIT compiler monitors method call frequency and compiles hot paths to native machine code, applying aggressive optimizations like inlining and escape analysis as it goes. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.